Welcome and thanks for joining this short lecture on NPUs and the future of Edge AI in mobile devices. Today, we'll explore how dedicated neural processing units are changing on device intelligence, why that matters for performance and privacy, and what developers and hardware teams need to focus on to bring real-time, efficient AI to everyday phones and tablets. Neural processing units are specialized chips built for low-power, high-efficiency AI inference, typically using systolic array architectures that multiply and accumulate weights in parallel, combined with on-chip high-bandwidth memory and quantization tricks like INT8. NPUs deliver trillions of low-precision operations per second while sipping milliwatts, enabling real-time on-device intelligence with minimal power draw. When we compare general CPUs, GPUs, and NPUs, the difference becomes clear. CPUs handle sequential tasks. GPUs excel at graphics parallelism, but NPUs are designed for matrix workloads and peak AI efficiency measured in TOPS per watt. That hardware focus turns captured data into fast, on-device processing and immediate real-time action, which is what enables smooth, power-efficient AI user experiences. Leading mobile NPUs from Qualcomm, MediaTek, and Apple show how vendors are turning this theory into products, with Hexagon engines, Dimensity NPUs, and Apple's Neural Engine, achieving 3 to 12 times acceleration over CPU or GPU, and enabling billion-parameter models on device. Manufacturers are already hitting multi-billion parameter ceilings today, driving a new generation of mobile AI capabilities. Practical on-device demos highlight these gains. NPUs enable 4K HDR video segmentation for instant object isolation, night mode denoising for clearer low-light photos, and 30 FPS face unlock for fast, secure biometrics. The result is reduced shutter lag, improved privacy because sensitive data stays on the device, and perceptibly snappier camera and security features for users. Speech recognition and translation show a dramatic shift from cloud dependence to on-device capability. Historically, voice required round trips to servers with latency and privacy risks, but modern NPUs can pre-fill and decode speech streams locally at high token rates, delivering instant responses, offline voice typing, and real-time multilingual subtitles while keeping user audio private on the device. Google's LiteRT runtime tackles real-world fragmentation by abstracting vendor differences and optimizing models for Android, selecting the best delegate whether Qualcomm's AI engine or MediaTek's NeuroPilot, and reducing inference latency by roughly an order of magnitude, which lets developers get predictable, fast NPU performance across a wide range of phones without reinventing platform-specific toolchains. Fitting generative models into 816 GB phones requires mandatory optimization steps, prune redundant weights, quantize from FP32 to INT8 to save space and compute, and exploit embedding sparsity to reduce memory footprint. When done carefully, these techniques preserve accuracy with minimal loss, usually under 2%, while maintaining high NPU throughput, measured in dozens of TOPS on optimized silicon. A key limitation today is the context window challenge. Edge NPUs can handle limited windows around tens of thousands of tokens, ideal for short tasks, while data center models support massively larger windows up to 1 million tokens for long-form summarization and deep reasoning. Hybrid execution that offloads heavy summarization to the cloud while keeping real-time tasks local is a practical compromise for now. Despite impressive silicon, a large share of mobile NPUs remain underutilized according to survey data, held back by toolchain fragmentation and developer inertia. The path forward requires unified APIs, better developer education with killer app examples, and clearer cross-platform tooling, so those idle accelerators can be unlocked for mainstream, high-impact use cases. Looking ahead to 2026-28, next-generation mobile NPUs aim to enable always-aware multimodal agents by packing 10-20 billion parameter capabilities into on-chip DRAM and sparsity-aware cores, all while staying within tight thermal and cost constraints. Think operating under a 5-watt thermal budget, and targeting silicon costs below $5, so multimodal, persistent agents can be practical on consumer devices. To conclude, we're at an NPU pivot where optimized edge silicon enables privacy-first, context-aware companions. The way forward is clear: optimize models, standardize tooling, and target edge silicon designs to unlock scalable, sustainable AI. This is a call to action for developers, chip designers, and product teams to work together and make on-device intelligence ubiquitous.